So, hello, welcome everyone. This is lecture 8th for the solid state physics. Okay, last time we studied the coherence length, London penetration depth, the type 1 and type 2 superconductors, and there's some graphical representation up till here. Today we're gonna discuss more about the type 1 and type 2 superconductors. Okay, so let's see. Type 1 superconductors also called the soft superconductors. Okay, so by definition, superconductor which strictly follow the Meissner effect are called type first superconductor. Okay, so what is the mean by following this Meissner effect? We know Meissner effect. We studied that below the critical temperature, the magnetic field inside the superconductor will be zero. That is called the Meissner effect. So the type first superconductors will follow strictly this rule. Okay, so if B equal to mu naught H plus M, then B will be zero inside, and here from here we will get H equal to minus M. Okay, and the graphical representation will be, if we put minus M here and H here, then this will be a straight line. Okay, so below HC it is the critical field, below SC it will be the superconductor, and above SC it will be a normal metal. We already studied about the critical field. Okay, some more representations here. Superconductor exhibits perfect diamagnetism in the type first below a critical field SC. Below critical field it will show the perfect diamagnetism. The type first superconductor will show perfect diamagnetism. Okay, so from here we also that if we plot resistivity with the field, then resistivity will drop down zero immediately below SC. Okay, and same if we talk about resistivity will temperature, then below TC it will drop down, resistivity will drop down. So basically type first follow strictly all the superconductor laws, but it's not the case in the type second. Let's study. These superconductors do not follow the Meissner effect strictly. That is, the magnetic field does not penetrate these material abruptly at critical field. Means it's not like the critical field is reached and abruptly the field came uh, into the superconductor. It comes gradually in the form of vortex. We will study what are vortex. Okay, so how it came, it's not just like it's greater than SC, then it will, the magnetic field will come automatically. It's started before SC and start penetrating gradually. So there are two critical fields here, the SC1 and SC2. Okay, so we will study from here. Below HC1, below SC1, if we plot, this is a superconductor and we are increasing H. Okay, so up to HC1 it will follow all the rules of the superconductor and it will call the pure state, and Meissner effect will be followed here. Okay, this is called pure state. But when the HC1 is reached, the material exhibits perfect divergence below SC1 and no flux penetration. No flux will penetrate through that, and B will be zero, as it is said in the Meissner effect. But greater than HC1, the flux begins to penetrate the specimen. Now, when the field is increasing greater than SC1, then the field inside the superconductor start to penetrate. Okay, we will so see them. First, let's discuss what the theory says. At H equal to SC dot means now the flux is increasing gradually, but when the critical field reached up to SC2, the complete penetration of flux occurs and the material becomes normal metal. Means at SC2 we will get the same state like this, normal state. Okay, but it's not like in the type of semiconductor. It was just at SC all the field penetrated the material, but here it will penetrate gradually. Okay, so what is vortex and how it is happening, we will see from this graph. Up to SC1 this is following the same. Okay, M equal to H, and it will cancel out all the magnetic field inside it and all the magnetic flux, so magnetic field will be zero, flux will be zero. But when SC1 it is greater than SC1, then M start to decrease and at SC1 there see, you see from here that below SC1 it is 0 inside, but when it reached SC1 there is some very small point size hole came into the material, means that is not hole, means the field start to penetrate from the in the material. Okay, and that inside that point is called the vortex. From there the field start to penetrate. So outside of vertex B will be 0 but not 0 at the vortex. So it's like a whirlpool in a pond, means when you place a hole inside a tub which is filled with water, then it will make a whirlpool and the water is starting to getting out from the tub. So you can analog it with that. So field start to penetrate. Now when we increase the field greater than SC1, then there will be more number of vertex. Vortex number will start to increase, and up to SC2. At SC2 we will see that there is that very much amount of the vortex will appear and all the field start to penetrate. Okay, and ultimately we will have B is not equal to 0 inside the superconductor. Okay, at that time we will say that it reached in the normal metal state. Okay, so this flux which came at the point of SC1 is called fluxon. The flux at SC1 will be called the fluxon. Okay, also called fluxoid, and value of this is phi equal to h by 2e. Here h is Planck's constant, e is charge on electron, and its value is 2.07 into 10 to the minus 15 Weber. We measure flux in Weber, that's why. Okay, hope it is understood. And this graph, this state is called mixed state, and greater than that it will be a normal state, and it is pure state up to SC1. Okay, so that's all about the type second semiconductor. Now we will study about the flux quantization. Meaning of quantization is that we study in the charge quantization, that charge is quantized, means n times E. Okay, so when the flux started to came out from here, then we will see that this flux coming out of the superconductor is quantized. We will see how it is quantized in the now. Okay, so it is quantized. Now we will study more about it, that how it is quantized. The magnetic flux passing through a superconducting ring, you can assume ring here, means when the field start to penetrate, then it will form like a ring structure, and if you take a ring separately, then it will also like that. Okay, so a ring or a hollow superconductor cylinder can have values equal to, is the value of magnetic flux if we passing flux through the ring of superconducting material, or it is hollow superconductor cylinder. So we are just applying external field in the superconducting ring. Okay, so what we see that according to the Lenz's law, it will oppose all the magnetic flux coming out from outside, and will make it zero, means net magnetic flux will be external plus the magnetic flux produced by the superconductor in the opposite direction phi sc, and it will be we will see that how it is nh by 2e. So according to this rule that flux is quantized, this flux, the phi n, means the net flux phi external plus phi sc, it is quantized, and it is nh by 2e. From h by 2e we know it is value of fluxon, we studied just before this, and n we will fluxon by this symbol phi naught, and phi naught, and n will be 1 2 3 4 5. So it is saying that flux is quantized in form of phi naught. Phi naught was h by 2e, which form at the SC1. So phi naught h by 2e, we place the values. Now we have value of fluxon in 2 units, measurement units, that is metric and CGS. So in the MKS system we know phi naught is h by 2e, where E is charge of an electron in coulomb. Whereas in CGS we measure charge in electrostatic unit, and that is 1 by E turns to C by E. So Hc by 2E. Here C by E is the conversion, E is in coulomb there in the down. Okay, it's just a conversion. So we will see that how it is quantized. So some physical interpretation. It is can be shown from this graph. Like just take the case that phi external, you applied a field from the external side, then there is a opposite magnetic flux produced by the superconducting ring to cancel out this. So up to a point it will cancel out totally, and with cancelling out there is increase in current in the superconducting ring. When this current reached to the up to the limit of critical current, then the current suddenly drops to zero. Current suddenly drops to zero, which drops phi sc as zero. Okay, and we see that our net magnetic flux is starting to pass, uh, because it can't increase from I more than IC, otherwise this superconductor will turns into a normal metal. So that's why it is opposing when the current reached up to the limit of IC, and after that it drops to zero, and we see that our net flux will be passed from here. When you are increasing, just increasing phi external, then up to a limit it is opposing. Then when it is reached to the IC, then it will current will drops to zero and phi sc drops to zero, and there will be a net magnetic flux in direction of this, which will be phi naught first. Then when you increase the magnetic flux more than this is phi naught, then you will see that it will again oppose the magnetic field. Means more magnetic field will be opposed by the Lenz's law accordingly, and it will again start increasing the current in it, and at the limit when it is reached to the critical current, it again drops to zero, and there will be a net increase in the magnetic flux, that will be 2 phi naught, and just it will follow the rule same, and it will 3 phi naught, 4 phi naught. That's how we can say that the net magnetic flux passing through this ring or any hollow spherical hollow cylinder of superconducting material is quantized in the form of phi naught. Hope it is clear to all of you. Okay, whoever is watching this video, so that's easy. I think if you have any doubt you can put in the comment section. Now we're gonna move forward. Okay, estimation of HC1 and HC2. In the second type of superconductor, we're gonna estimate the values of SC1 and SC2. So first to estimate SC1, we know that at SC1 we will get a vortex, and that gives us the field which is phi naught. Okay, this is consider this is the bigger case. So it is superconductor, and at SC1 there is this vortex from where in it the field is passing through it. Okay, so we can measure SC1 using London penetration depth. We will see how we will measure it. So consider this as this hole. Now in the center this represent this. Okay, so we see that B is 0 here, B is 0 here, but B is not equal to 0 here, because that is the vortex. So B equal to 0 here, B is 0 here, vortex here. Okay, at H equal to SC1. Okay, so we will represent the field as this. If we represent here, then we will see that it is 0 here, 0 here, 0 here, 0 here, but as we reach towards the vortex, it start increasing, and inside the vortex it is SC1. Inside the vortex it is SC1. So this will be the representation, graphical representation, and we see that the dimension of the vortex is very small. It is in the nanometer, 10 to the power minus 9 nanometer, and we know that what is London penetration depth. It is when this SC1 drops to divide by epsilon value, SC1 by epsilon value, and this will be lambda. This distance will be lambda from here. So this is called London penetration depth, and we see that lambda measures in the micrometer range, and vortex is very small. It is just showing that it is large, but it is not large. It is very small in the nanometer, and lambda is very large in the micrometer. it's 1,000 times than this vortex dimension. So we can say that this is also lambda, because it will be in don't make any much difference, it will also be approximately lambda. Okay, so from here we can measure the flux. The flux will be in the B into area. So B is SC1 and area is pi lambda square. So from here we can measure SC1 will be phi naught divided by pi lambda square. Okay, so you measured the SC1 field using the London penetration depth, and here phi naught we know what is, it is flux on, which is h by 2e, or fluxoid we can say, and lambda is given, then you can measure. Okay, same the SC2 can be measured, and here it will be measured in the with the use of the coherence length zeta. Okay, and result will come like this. You will try to solve it by yourself. This will come just like same as we came above. The flux will be SC2 pi zeta square, then this SC2 can be measured this way. Okay, now in the today's lecture it is last. Let's study about the thermal properties. Okay, for the materials superconductor. So first of all, let's discuss about the entropy. What's the entropy? We all know that entropy is a measurement of spontaneousness. Okay, so in the general formula is S equal to KB, natural log of W. KB is Boltzmann constant, and W is number of microstates, or we can say the thermodynamic probability. So what is number of microstates? It is just simple, like if there are n particles, then the number of ways it can be arranged can be given as number of microstates. Okay, they can be arranged in many number of ways in the states, energy state, or whatever state it can be. So that number is called thermodynamic probability, or W. Okay, for example, there are 10 electrons, then at T equal to 0 Kelvin we see that there are only 5 states required to fill these 10 electrons. Okay, so W will be 5, but when T is not equal to 0 Kelvin, then it can be placed in more number of states than 5. So that's how the probability varies and the W varies, and the spontaneousness, or which can say it as entropy, vary according to the number of states. Okay, so let's see the first graph, the entropy and the temperature in the superconductor. We see that up to the critical temperature, the entropy decrease in the linearly, but below the critical temperature, when the superconducting nature comes into play, then it drops faster as compared to before. Drops faster. So how? What's the reason behind dropping the entropy faster? So we see that below T less than Tc, S decreases faster. This is because of the formation of Cooper pairs. This is because the formation of Cooper pairs. What are the Cooper pairs? I already told you in the last lecture. That was the bound state of two electrons whose net spin is 0. Okay, and they are bosons. They are bosons. So what is happening here? So the entropy is decreasing. That's because of formation of bosons. Okay, means when the bosons form, bosons are those particles which don't follow the Pauli exclusion rules and or the principle, which means that they can be more than one in the single state. Okay, so Cooper pairs can exist, more than one Cooper pair can exist in the same state. So we see that total number of state will be required less for the same number of particles, and as W decreases we see that S decreases. Okay, so the reason is this, that's why S decreases faster, because of the formation of Cooper pairs. In the BCS theory we will study how the Cooper pair actually works, and how they form, or what is the coherence length and all. Okay, now just keep in mind that because of the formation of Cooper pair, we see that S drops faster, because they can be there is decrease in W. Okay, so the next is the thermal conductivity. We know the thermal conductivity, the way the heat conduct inside a metal or anything, that can be represented using the thermal conductivity. Okay, from graph we see that thermal conductivity also drops faster below the critical temperature, means in the superconducting state it drops faster. So what's the reason? T less than Tc, the thermal conductivity decreases faster. It is less than the normal metal. So if here is a constant of thermal conductivity and his temperature. So this happens because Cooper pairs can't carry the thermal energy. Below this, Cooper pairs will be formed in the superconductor, and they can't conduct the thermal energy. So, for example, we have 1,000 electron, normal electrons, T greater than Tc. Below T less than Tc, T less than Tc, then let's say that 100 Cooper pairs are formed. Okay, so the remaining electrons will be 900, uh, or we will say that 100 Cooper pairs, 100 electrons form the Cooper pair, not 100 Cooper pair, 100 electrons form the Cooper pair, that will be 50, and the remaining electron will be 900 normal electrons. So there is less number of electrons available to conduct the heat, to carry the thermal energy. So because of the less number of what we can say that the conducting or the carrier carrier of heat are less, that's why we see that there is decrease in the thermal conductivity. Okay, so we will end our lecture today from here only. Okay, so tomorrow we will discuss about the specific heat and BCS theory and all, or the Josephson function, they are still remaining. So we will have 2 or 3 lecture more for the superconductor. Then this whole will be ended. Okay. So just follow the lecture series and the day-to-day routine, and it will be very easy to crack any exams related to physics. Okay, thank you. Bye.